Okay, we're going to continue on here, and we're talking about something chemistry. We were talking about bonding, I believe, if I am not mistaken. So last time we started talking about bonding, remember there's sort of two types of bonding. There is, again, ionic bonding, which is always between a metal and a non-metal. And that pretty much is how you can recognize that it's an ionic bond. As soon as you see really that combination together, you definitely will know it's ionic. And always in that situation, because of those periodic trends we talked about, we are always going to get a transfer of electrons from the metal to the non-metal. That is, again, going to create our ions here. Our cation and is positively charged, and our anion, which is negatively charged. Remember, sort of in an ionic compound, our bond, there really is no sharing of electrons there. So what's holding that together is the opposite attraction between the positive and negative charge there, which is sometimes referred to as electrostatic attraction. And we can also see covalent bonding that we talked about. And covalent bond is typically between two nonmetals. And because of those sort of periodic trends that they're very similar to, neither one of them wants to give away its electrons. So it's going to basically share electrons. So there is some type of sharing of electrons that's occurring in a covalent bond. That sharing could be equal. That sharing could be unequal, but there is, again, some aspect of sharing going on pretty much in that type of bond. We could really represent bonding by using Lewis dot symbols or electron dot symbols, which is essentially the symbol and one dot to represent the number of valence electrons there are within that atom. Also, you could get the valence electrons, which are the ones that are the highest energy electrons. They're involved in bonding. You could get that from the electron configuration, or probably super easier, it is equal to the group number. So remember that the valence electrons equals the group number on the periodic table. So everybody in group one has 1, 2, basically 3, 4, 5, 6, 7, and 8. Again, we don't really do anything with the transition metals, so you don't have to worry about that in terms of bonding. The one exception, obviously, is, as we talked about, I think last time, is helium there in group 8. Again, it only has 2 total electrons, so obviously it cannot have 8 valence electrons, but it does have 2. Everybody else there will have 8. Also, why, as we talked about with hydrogen, which comes before helium on the periodic table, it should only have 2 electrons total, no more than that. Otherwise, again, it will it only needs to really get to helium, so you should never have more than 2 electrons for hydrogen. Everybody else pretty much got to shoot for that 8. The whole purpose of bonding, if you remember, as we talked about, is pretty much for everybody to end up here on the group 8 noble gas electron configuration. Again, they don't become those elements, but they do become like those elements in terms of their electron configuration, and those elements are extremely stable. So ionic bonding, covalent bonding, the whole purpose is for everybody basically to end up there. They're sort of achieved 2 different ways. As we talked about in ionic bonding, it's achieved by losing and gaining electrons. So when a metal loses electrons, it will actually back up on the periodic table, back to the noble gas that comes right before it. When the nonmetals gain those electrons, they will actually go forward on the periodic table there to the noble gas that comes after them. In covalent bonding, that is achieved through sharing of electrons. So again, by sharing those electrons, it will allow everybody basically to get 8 electrons around them, which again is going to make a really stable bond, except for, again, hydrogen, which will share to get to 2. And again, not more than 2 in that case. I think we left off talking about electronegativity, if I am not mistaken. And electronegativity is the ability of an atom to bring electrons towards itself. And when you look at the periodic table, it increases as you go up and to the right and decreases as you go down and to the left. And fluorine is the most electronegative element that you could have. And it really is sort of electronegativity, which determines, you know, how those electrons are going to be shared. You can use electronegativity to determine what type of bond you have, if you have an ionic bond, a polar bond, or a nonpolar bond. But really, you don't need it for the ionic bond, as we might have mentioned last time. And that's because all you need to know is metal, non-metal, it's ionic. You really don't need to worry about sort of the difference in electronegativity. But for polar bonds or non-polar bonds, and again, polar bonds is unequal sharing of those electrons. Non-polar bonds is equal sharing of those electrons. We really could use the difference in electronegativity to help us determine between those two. And that's really what you should use it for. The ionic sort of situation is not perfect. So there's sort of a difference in the number, and you'll get something that's not always the right number, but metal, non-metal is really all you need to worry about. Any questions on that stuff we got to last time? So going here. All right. So I believe we talked about this last time, right? Yes, if I'm not mistaken. Yes. All right. So, and we talked about the difference between those. So I think this is where we were at, if I'm not mistaken. So as I mentioned, electronegativity is that ability of an electron to bring or an atom to bring electrons towards itself. It is really the overwhelmingly thing that we want to look at when trying to decide how those electrons are going to be shared. And Pauling actually came up with sort of a scale for electronegativity. And Pauling's scale is 0 to 4. And 4 is the most electronegative element you could have. And 0 is, not so much, right? So one of the things that we use to help us, like I said, decide how the electrons are going to be shared is what is sometimes referred to as the difference in electronegativity, delta En, and that's basically the difference in electronegativity values. And basically, if you calculate between two atoms within a bond, their difference in electronegativity, that will help you determine what type of bond you're dealing with. So if you calculate the delta En, the difference in that electronegativity, and you get a value that's anywhere from 0 to 0.4, that is considered a nonpolar bond, which basically means we're going to get some equal sharing of electrons, basically. So equal sharing. If you're above 0.4, which technically would be like 0.5, to below 2 difference, that is considered a polar covalent bond, which is unequal sharing of electrons. And typically speaking, if you get a difference above 2, you're going to get pretty much no sharing. You're going to get an ionic bond that's going to happen in that case. So that sort of cutoff of above 2 is what I was talking about, that you really don't actually need these values to figure that out. Again, metal, non-metal, ionic. There is going to be a number of combinations of a metal and a non-metal that may actually give you a difference in electronegativity values of less than 2, but they're still ionic. So that's why I would say I wouldn't even worry about sort of those values for an ionic bond. I would just go with the metal, non-metal. Now, when we talk about the other sort of ones that are non-polar equal sharing of electrons or polar unequal sharing of electrons, that is both covalent bonding, as we're sharing electrons in that case. Now, sometimes when you get a delta En or a difference in electronegativity of exactly 0, They will sometimes classify that as a pure covalent bond. And a pure covalent bond is still a nonpolar bond, but it is like as perfect equal sharing as you could get, basically. So it's like a perfect equal sharing situation. It's still considered a nonpolar bond. A reminder that when we have a nonpolar bond, it is essentially a neutral bond, right? Because we've got equal sharing of electrons. So if we have a nonpolar bond between these two guys, that bond right there is essentially going to be neutral. There's no like positive side or negative side because overall the electrons are being shared equally. When we have a polar bond, a reminder that we do get that unequal sharing of electrons, which does create a bond that is sort of charged. One side is, for example, partially negative, one side is partially positive, and the side that's partially negative would be the side that is more electronegative, right? It will be where those electrons are hanging out basically more than the other side. As we, I think, talked about as well last time, they are partial positive charges and partial negative charges because there is still some aspect of sharing happening there. So the electrons haven't fully jumped from one side to the next. They're still hanging on, but they're not hanging on equally between the two. And again, that's what creates these sort of partially charged parts to this bond. And that's really important for later on in some chapters of how, for example, molecules interact with each other if they have that sort of charge or not charge, and that will allow them to sort of interact. Any questions on that there? So let's take a look at this table here, or a table like that. Actually, we'll go with the bigger one. It's got all the numbers on it. Why not? Obviously, these numbers would be provided for you if you needed them. But actually, we'll back up to this one. We could probably borrow this one for this. Will work for what we have. Yeah. So let's take a look at the three sort of examples of bonds that we talked about. We had our sodium chloride again that we looked at. We had our HF, and we have like our F2. And again, when we look at these guys here, we can use the difference in electronegativity values to help us decide what type of bond is going on. Once again, if I go to the table, I can see fluorine is 4 for its value, and this guy is 4 as well. So to calculate the difference in electronegativity, we're just going to simply take 4 minus 4, and that's going to give us 0. And that 0 obviously falls between 0 and 0.4 on that little scale that we just talked about, and that's going to make us a nonpolar bond. It really is a pure covalent bond that's going to be like perfect equal sharing of electrons between those two because really they're the same element. If we come over to our hydrogen here, hydrogen onto there is 2.1, fluorine is 4. By the way, when you do this sort of subtraction, you just take the larger number minus the smaller, so you always get a positive number. It's really the difference, so you could do it either way, but just do it so you get a positive number. So we'll take our change in electronegativity, 4 minus 2.1. I'll go with 1.9 in that particular case. 1.9 puts us between 0.5 and less than 2, and that would tell us that that is a polar bond. Remember, we could draw those bond dipole arrows that will actually point towards the more electronegative guy. And in this case, it would point towards the fluorine, which is more electronegative. And again, the back part of that arrow that makes kind of like a plus sign will be to the sign that's more positive. So the fluorine here in this bond would be more negative, and this guy would be more positive. Once again, that arrow is what is sometimes referred to as a bond dipole arrow. And again, it always points to the more negative side, and the other guy is where the positive side is there in that particular case. Now, lastly, here we have sodium, which is 0.9 on the electronegativity scale, and chlorine, which is 3. So once again, just taking the larger number minus the smaller number, 3 minus 0.9, that's going to give us a 2.1. That 2.1 is above 2 technically, and that would tell you that it's going to be an ionic bond. But as you could maybe see, if you just kind of look at some combinations here, it is definitely possible, that you could get less than 2. For example, if you maybe pop those two guys together and subtracted them, you get less than 2, but it's still an ionic bond. So again, I wouldn't even worry about electronegativity for ionic, but you definitely could help you for polar or nonpolar. Question on how to do that there. All right, so let's just try some here. Are the following bonds ionic? Is it polar or nonpolar bonds? And it's the bond between, say, carbon and oxygen, the bond between sulfur and oxygen. Let's do carbon and sulfur. Let's also do carbon and hydrogen. Let's do a little lithium and chlorine. All right, so take a moment to calculate the difference in electronegativity and determine, is it ionic, polar, or nonpolar, each of those bonds. If it is a polar bond, draw the arrow pointing in the right direction. Yeah, the dipole arrow. Okay, so let's take a look. So once again, these values would be provided for you. You just want to kind of find the two ones that are within the bond. So we'll start with the carbon and oxygen. So from the table there, we can see it's 2.5 for the carbon and 3.5 there for the oxygen. Once again, we're just going to take the larger number minus the smaller. So that would give us a difference in electronegativity of 3.5 minus 2.5. That will give us a 1 as our difference. That is going to put us here between those numbers, the 0.5 and below 2, and that would tell us that this bond here would be a polar bond. Now, because it's polar, I could draw that dipole arrow. It should point towards which element? Should point towards the more electronegative, which in this case would be the oxygen, right? So it should actually point in that direction. The oxygen would be more negative than the carbon, as more electrons are kind of hanging out on the outside of the bond. Question on that one there. Between sulfur and oxygen, sulfur 2.5, oxygen still 3.5. That is, believe it or not, can give me the same difference there. Difference in electronegativity, 3.5 minus 2.5. That's going to be not 0. That's going to be 1. And the difference there again will put us back into there. And this would also be a polar bond because of the difference in electronegativity. Again, in this case, we would also draw the arrow pointing towards the oxygen, as it is more negative in this bond. When we look at carbon and hydrogen, carbon is 2.5, hydrogen is 2.1. Difference in electronegativity, 2.5 minus 2.1. That is 0.4 difference. 0.4 difference actually puts us right here. And that's really the reason for the 0.4 cutoff, because that's an organic type of bond, and our organic molecules are nonpolar. And it would actually be a nonpolar bond in this case. Because it's a nonpolar bond, we do not draw the arrow. The arrow, again, is only for polar bonds, because in a nonpolar bond, they're going to be sharing those electrons equally. Again, you can think of it like a neutral bond. There is no negative side or positive side in that situation. Question on that one. All right, let's go carbon sulfur here. So carbon 2.5, sulfur 2.5. That is going to give us a difference in electronegativity of 2.5 minus 2.5. That is a 0. And that would then obviously put us in a nonpolar bond. This also would be considered a pure covalent bond, as it's like perfect equal sharing of electrons in that case. And again, we would not draw a molecule, I'm sorry, an arrow here, as it is a neutral bond. Now, that brings up a good point, that is basically two different elements that actually share the same electronegativity, and that can happen. So if you have two elements that are the same, obviously within a bond, they're going to have the same electronegativity, but you could also have two elements that share the same electronegativity that are different. The relationship that comes from is what is sometimes referred to as the diagonal relationship of on the periodic table. Carbon is here, sulfur is there. They're like diagonal of each other, not directly below, but kind of one over. Same thing over there with nitrogen and chlorine. You'll kind of see that happen as well. One is further up, but one's further to the right. So they kind of cancel out their differences in terms of electronegativity, and they actually end up with kind of the same value. So diagonal relationships sometimes occurs, and you can get two elements that are different elements, but actually do share the same electronegativity values. We look at lithium here, which is 1. Chlorine, which I wrote all over, is 3 in this case. So difference in electronegativity going to be 3 minus 1, which is 2. And that is going to be an ionic bond. But as I mentioned before, don't even really need that. That's a metal. That's a non-metal. That's all you need to know for those two to be able to really know that it's ionic. And that's how I would go with it for those two. Question on how to use electronegativity values there. Now, do you always need the actual values? The answer is no, you really don't. You can pretty much make a pretty good estimate just using the general trend in electronegativity, especially, for example, if you're looking at something that's either in the same group on the periodic table or the same period on the periodic table. We look at our carbon-oxygen bond from earlier. They are in the same group on the periodic table, and oxygen is actually further to the right. And I'm sorry, they're in the same period on the periodic table, and oxygen is further to the right, and that would make it actually more electronegative and will yield you a polar bond. You don't even really need the numbers. We could also look at our sulfur and oxygen sort of combination. That guys are in the same group, and oxygen is further up in the group than sulfur. And that also will get you a polar bond and a difference in electronegativity. So if you're comparing two elements that are in the same period on the periodic table, are the same group, and they're away from each other, which they most likely would be, it probably will be enough to give you a polar bond in that case, and you can pretty much make a pretty good estimate as to that. Any questions on, again, using that there? Okay. So as I mentioned, atoms with really widely different electronegativities will tend to make ionic bonds. And again, that's really because as you get somebody on the left-hand side of the periodic table with somebody on the upper right of the periodic table, there's going to be a pretty big difference in that electronegativity values. And that's going to make, for a lot of reasons, the electrons jump from one to the next, from the metal to the non-metal. But when you crowd everybody here in the non-metal region, like we have with covalent bonding, everybody has similar electronegativity values, not enough to cause the electrons to jump from one place to the next. They're just going to actually share electrons in that particular case. And there's from your book there, are similar in your book there, the cutoffs that we talked about there. Basically 0 to 0.4 non-polar, equal sharing of electrons, 0.5 and above to below 2 polar, more than 2 usually going to be ionic. Now, when we have some sharing that is like 0.4, is it like perfect equal sharing? It's not. There is some unequal sharing happening, but it's not enough to be considered totally unequal sharing. So there's sort of a limit there. Any questions on that there? All right. So now what we're going to talk about is drawing Lewis structures for covalent bonds and covalent molecules. And by the way, what we just talked about there with the electronegativity difference, it was sometimes referred to as bond polarity. So difference in electronegativity basically tells you, in most cases, just between these two atoms, how the electrons are going to be shared equally or unequally. It does not always tell you in the entire molecule how everybody's going to share the electrons, but it tells you how just between those two things, which is why it's sometimes referred to as bond polarity, how those two guys are going to share the electrons. We will talk about it a little bit later, but in some cases it actually will tell you the whole story, but in other cases it will not. So it kind of depends on the situation. If that's your question, we'll get to it. Yeah. It does affect the polarity doesn't necessarily affect the shape of it, but it does affect how many types of electrons you have around the central atom, stuff like that. That affects the molecular polarity of it, as we'll talk about. But also the types of electrons that are around it, the central atom, as we'll talk about, affects the actual shape of it. Yeah. All right, so I would recommend that you perhaps follow these instructions on how to draw these Lewis structures, because they will get you to a pretty good picture when it's all said and done. If you try to do it like a lot of people do, and I call it kind of like do it by piecework, like, you just kind of take all the individual elements and Lewis dot symbols and try to figure out how all the electrons kind of come together, usually you're going to end up with a picture that's probably got not the right number of bonds, too many electrons, not enough electrons. So what we want to think about as we're doing this is we just want to kind of distribute the electrons as sort of equally to everybody as possible. And that usually will end up with, a pretty good structure. So one of the first things that you want to figure out is, if you're not sure, how everybody is sort of hooked up together, how everybody is sort of bonded together. And that's sometimes referred to as the skeletal structure. So to help you make that decision, there are a couple of rules that you want to follow. One rule is usually the least electronegative atom is the one that's in the center. So we usually want to put the least electronegative atom in the center. I would say probably for you guys in this class, and in a lot of cases, there usually will just be one guy in the center and like everybody else is sort of attached to it. That's not always the case. It is possible to have multiple center atoms and multiple things attached, but probably most of the things that you'll probably come across until we get to maybe some organic things, but it will be like there's one guy in the middle and then like everything else is sort of attached to it. That means that hydrogen and fluorine should never be in the center. That's because fluorine, as we just saw, is the most electronegative element, so it should not be there because it's not the least. And the reason we shouldn't put hydrogen in the middle is what's going to happen if we do? Like if I laid up hydrogen in the middle and then put some other things around it, what happens to my friend hydrogen? It's got like way too many electrons. Yeah, so never ever again should we put hydrogen in the middle. Hydrogen again should simply be on the outside, kind of looking like that, pretty much one line or one bond to it. And again, never should be in the middle, otherwise it's going to end up with too many electrons. Probably the most important thing that you need to do is really number 2, and that is to count up the total number of valence electrons in the entire molecule or ion. And again, we could get the valence electrons from the periodic table and the group number. Now, if you come across something that has a charge, like a polyatomic ion that we talked about, you do have to take the charge into account when you're adding up everything. So if we have somebody that has a negative charge, we need to add to our total. So if we have a negative overall charge, we need to add those electrons to our total. And if we have something with a positive charge, we need to, it's actually positive there, we need to subtract that positive charge from the total. So you do have to adjust it. Again, if you don't do that, you will be off. You'll have not enough electrons or too many electrons, so you do need to adjust it. If it's obviously neutral, you don't have to worry about that. You just have to get all of the valence electrons. Once you have sort of the logical arrangement of how everything should be put together, and once you figure out how many electrons you need in your picture, and that number is really important because when you're done with your picture, you got to hit that number on the nose. You can't have any more or any less electrons. It has to hit that exact number with your picture. What you want to do, which is again a very common mistake that people make, is they want to double bond and triple bond right out of the box because, again, it looks more chemistry like, and that usually leads you to a pretty bad structure and stuff like that. So you do not want to double bond or triple bond out of the box. You want to take whoever's in the middle and you simply just want to make one single bond to everybody. Remember that one line represents 2 electrons, right? So that represents 2 electrons in this case. You want to count up how many electrons you just used. So each of these lines, 2, 4, 6 electrons. I basically just used in my made up picture. All the remaining electrons go on the outside atoms first, in pairs of electrons. So these are dots on the outside atoms, and then you work your way in. So always on this deal at this point, we want to work outside in to do so. So we would go around until everybody obviously has 8 valence electrons around them. We would put them on as dots of electrons. And if you filled up all the outside atoms with pairs of electrons and you still have electrons to go, then you go to the center atom. So again, working outside in, and that's where you lay up a couple of dots perhaps, also comes on as pairs of electrons. At this point, once you get to the center atom, you should be out of electrons, or something's not so right in this class for sure. You definitely should be out of electrons at that point once you put them onto the center. Once you've done that, what you want to do is you want to go around everybody and you want to make sure that everybody has met that octet rule, that everybody has 8 electrons around it, except for obviously hydrogen that should only have 1 or 2 electrons around it. It is at that point that if somebody has not met the octet rule, that's when you should try a double bond to fix it. So you want to kind of think of a double bond or even a triple bond as an effort to fix somebody that has not met the octet rule. So you would make perhaps 1 double bond and hopefully that works. If not, then if you have an option for a second double bond, you would want to make a second double bond at that point. If by some chance all your double bonds doesn't work, then you should move to your triple bond. So that's sort of the order that you want to do. You want to start with single bonds, and then at the end there, if somebody doesn't have 8, you want to try to fix it with a double bond. And if you cannot fix it with a double bond, then you want to go to a triple bond. So again, that's sort of the order at which you want to draw these things. Any questions about there? All right, so let's do one here together to see these steps in action. So we have NF3. So the first thing I'm going to do is actually just calculate the valence electrons. So we got 5 for nitrogen, right? Because it is group number 5 on the periodic table. I have 3 fluorines. Each is group 7 on the periodic table. It's a lot of math for late at night. It's 21 and 5 is 26 valence electrons there. So again, that number is really important because I have to hit exactly that number when I'm all said and done. So the next thing I want to think about is, what is the logical arrangement? Well, I have 1 nitrogen and 3 fluorines. I would say in most cases, if you have 1 element and 3 of something else or 4 of something else, probably the 1 guy goes in the middle. Yeah. I know he also should go in the middle because between nitrogen and fluorine is more electronegative, right? So we just talked about fluorine cannot go in the center. So it has to be nitrogen, which is the least electronegative in the center. So I'm going to do a nitrogen in the center. I'm going to put some fluorines around it. And to answer maybe the question you might have, yes, it doesn't matter. You could throw the fluorine up on top if you like. It don't really matter if you want top or bottom there with that fluorine. I'm going to do 1 single bond, and I'm going to show that with lines to represent those bonding electrons. I did 3 lines in this case. Each one represents 2 electrons. That is a total of 6 electrons I basically just put on my picture. I now have about 20 electrons still to go. At this point, again, we're going to work outside in. So pairs of electrons, so pairs of dots. So 2, 4, 6. That guy is full. 8, 10, 12. That one is full. 14, 16, 18. At this particular point, I just put another 18 electrons up there. I still have 2 electrons to go. Everybody on the outside is filled, so now we go to the center and we put them on as pairs of electrons. At this point, I have now put on my picture the 26 electrons that I need. Last thing I want to always check is to make sure everybody is happy in terms of the octet rule as well. So if we look at this fluorine on the right, 2, 4, 6, and 8. So he's good to go. This one's identical, 2, 4, 6, and 8. This one's also identical, 2, 4, 6, and 8. And when we look at the nitrogen, 2, 4, 6, and 8. Everybody has 8 valence electrons. And everybody will be happy with a little highlighting going on there. Yeah. Any questions on that there? Okay. So again, you want to kind of follow these steps. You want to think it. You really want to think of the electrons as not necessarily belonging to anybody, but again, we kind of want to distribute it as equally as possible. And again, that usually will get you to a pretty good structure when it's all said and done. Any questions? So why don't you try this one? Why don't you try NO3 minus? So that's nitrate. And see what you come up. Okay, so let's take a look, see how you're doing on this one. Again, we're going to kind of follow the same procedure here. I'm going to get the valence electrons, which is really an important number. So once again, nitrogen is group number 5 on the periodic table right there. That means it does have 5 valence electrons for our nitrogen. We have 3 oxygens, which are each group 6 on the periodic table right next door. And once again here, I do have a negative charge, which means what do I need to do with that? So when we have a negative charge, did we lose or gain electrons? Gain, right? So I do need to actually add that to my total. Otherwise, I'm going to be short in this case. So because of the -1, I do need to add one more in there. Again, otherwise you will be a little bit short there. That's 18, 19, 24 valence electrons. Again, if you had a positive charge, you would need to subtract one because it lost electrons. So again, that's really important to sort of adjust the total in that case. Well, when we look at nitrogen and oxygen on the periodic table, they are right next to each other in the same period, which means if we go this way, oxygen is actually more electronegative. So clearly here, nitrogen should be in the middle. By the way, once again, just logically thinking about it, you got 1 nitrogen, 3 oxygens. Probably that, again, that one guy is going to be in the middle in most cases, not always, but in a lot of cases it will be. So we're going to rearrange this here. Just going to kind of put my oxygens around it. And just like in the first one, it doesn't matter if you put the oxygen on top or bottom there in the middle. We're going to do our single bond to everybody. So a bond there, a bond there, a bond there. That again is 2, 4, 6 electrons that I used. That's going to leave me 18 electrons, I hope. Those again are going to go on the outside in pairs of electrons. So 2, 4, 6, 8, 10, 12, 14, 16, and 18 electrons. I am out of electrons at this point. Is everybody good in this case? No, which one's not good? It is the nitrogen. It is actually short, right? So if we look around at our oxygen here, that is 2, 4, 6, and 8. All the oxygens are basically the same, so they all have 8 around them. But when we get to nitrogen, we got 2, 4, and 6 only. So it is short. It has not met the octet rule in this case. We have already obviously distributed all of our electrons. So we need to try to fix this. So can I fix it by just putting some dots there? I cannot, because why? Yeah, I now have 26 electrons, right? And my cutoff limit is 24 for this. So we can't just put electrons on to fix it. This is the case where we want to try to fix it with a double bond first. Now, does it matter which oxygen I double bond at in this particular case? It doesn't, because they're all the same. They're all basically identical oxygens. Whichever one you like, you could double bond. Can I just throw a line down? I cannot, for the exact same reason. I now have 26 electrons. And by the way, the oxygen on top would then have 2, 4, 6, 8, and 10 electrons. Doesn't have the same ring as the octet ruler there, right? So too many there. So when we're trying to fix a situation like this and we need to make a double bond, and by the way, when you need to make a triple bond as well, what you actually need to do is actually just grab a pair of electrons. And what you're going to do is essentially take those pair of electrons and you're going to bring them in to make that double bond. So you're just going to kind of bring those electron pair in to make that double bond. The result of that is I will now have a double bonded oxygen on top, because that's where I decided to do it. I will have still the single bonded oxygens on the right and left side. And now I could put a little bracket around it to make it all pretty looking, because it is an ion. So typically we do put brackets around it and the charge on the outside when we draw Lewis structures for anything that has a charge. But more importantly, what I have just done is I hopefully have fixed the problem. So let's make sure I did. That is 2, 4, 6, and 8 electrons for the oxygen on top. So it's good. That is 2, 4, 6, 8 electrons for that oxygen. So it's good. That is 2, 4, 6, 8 electrons for that oxygen is good. That is 2, 4, 6, 8 electrons for the nitrogen. It is good. I still only have, if I go around, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 electrons total. So I have still 24 electrons. I have fixed it by making a double bond in this case, and that would be the proper structure without all the highlighting on it. It would be the proper structure in that case. Question on that there. Now, could I have double bond to the right? The answer is absolutely. You could have double bonded to the oxygen to the right. And if you did double bond to the oxygen on the right, you would end up with a double bond on the right, and everybody else would still be single bonded. And of course, you could have double bonded on the left if you chose to do so. And you would have had a double bond on the left if you did that guy, which is, again, perfectly fine to do. All three of these structures are actually related to each other. These are what are known as resonance structures. Resonance structures basically happen when you have a situation just like this, where frankly you have more than one option as to where you could have done that double bond. The true reality is those double bond electrons are what are referred to as being delocalized, which means they're just moving around, which means at any given point, they could be over here at this oxygen, could be up there at that oxygen, could be over there at that oxygen. They're moving around, so they really could be located at any oxygen at any given point. One Lewis structure by itself may not perfectly describe what's going on, so you can actually draw three equivalent structures, and they're related to each other as known as resonance structures, usually with these kind of arrow headed in both directions between the structures is usually what you see. Do you have to draw all the resonance structures? The answer is no, unless the instructions ask you to do so. But if the instructions don't ask you to do so and ask you just to draw the Lewis structure, you could draw any one of the three, and that's perfectly fine. So any one of the three would do. But again, if you happen to come across an instruction that said draw all the possible resonance structures, then technically speaking, you're supposed to draw all three of those. Any questions on that there? All right, let's try a few more here just to make sure. Why don't you draw H2S? Why don't you draw SO2? Why don't you do a little CO2? Why don't you do a little CO3 2 minus and N2? So draw up some structures for each of those and see what you come up with. Actually, we'll do one more here. Let's do NH4 plus. All right, so take some time, draw them up. You need to take a break, you could break as well, and then come back and work on it, whichever way you want to do it. Okay, so let's take a look at some of these here, see how you're doing. Again, we'll start with the top left here. I'm going to calculate my valence electrons. So hydrogen is 1, and there's 2 of them. So that's for our hydrogen. Sulfur is group 6, which means it has 6. So that is 8 valence electrons. We clearly know, right, hydrogen should never be in the middle. So we're going to go with sulfur there in the middle. Hydrogen could go on the sides. Once again, we're going to do our single bond. That's going to use 2 4 electrons. I now have 4 more to go, right, after I did that. So I got 4 more. Do I put dots on hydrogen? I do not, right? So remember, never, ever, 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 ever do that. Hydrogen is actually full, right? It's got 2 electrons on each side. That is essentially what hydrogen should always look like, just like that. No dots, nothing like that, one line basically. So what's left is then we're going to go to the center and go 2 and 4. At this point, we now have put all 8 electrons on it, and everybody is good. Hydrogen has, again, only 2. This hydrogen has only 2, and the sulfur 2, 4, 6, and 8. Everybody has 8 valence electrons around it, and a total of 8 total electrons as well. So once again, no hydrogens that look like this, yes, or triple bonded, none of those things. Yeah, so just a single bond hydrogen. All right, next one, we'll go right next door, which is SO2. Now again, 6 for the sulfur from the periodic table. There's 2 oxygens each is group 6 for our oxygen. That's going to give us 18 valence electrons. Once again, if we look at the periodic table, sulfur and oxygen are in the same group. Oxygen is further up, which means it's more electronegative. That would tell us that sulfur should go in the middle. Again, just logic as well. One sulfur, 2 oxygens. Probably that's the guy in the middle. So we're going to do sulfur in the middle. We're going to do an oxygen and an oxygen. We're going to do a single bond. That is 4 electrons we just used there. That's going to get us about 14 more to go. Once again, we're going to work outside in to do that. So 2, 4, 6, 8, 10, and 12. At this point, I have 16 electrons that I've put on this thing. I still have 2 more to go, right? So I still got 2 more electrons to put on there to get to 18. They go as dots on the central atom, and that is how they get there, by the way. They do not double bond on both sides or anything like that. They actually get there with the dots. Now we want to make sure that everybody is good. Is everybody good in this case? Which one's not good? It is the sulfur. Sulfur has only 6. So this is a situation where we can try to fix it by making a double bond. It does not matter, again, which one that you choose. But again, if you count up, sulfur has got 2, 4, and 6 only. So it is short. It needs 8. So I'm going to double bond here on the left. And a reminder that when we do a double bond or even a triple bond, we're going to take those electrons in to do so, to make that double bond. That, in this case, will give me a double bond there on the left. Did that fix it? Sulfur better now? It is. It actually has 8. That is actually good. We're actually good here. Everybody has 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Everybody has 8 electrons around it. This is also one that you could have done a resin structure for. You could have absolutely have double bonded the other side. And you would end up with a structure like that. So again, either one would have been perfectly fine, as they are resin structures of each other. Any questions on that one there? Can't tell you how many people will have double bonded both sides of this with no dots or anything like that. So again, make sure you follow sort of the order there, and it should get you to a good picture. All right, CO2. We got 4 for the carbon, 2 times 6 for the oxygen, right? That's going to give us 16 valence electrons. Once again, if we look at carbon and oxygen, they're in the same period on the periodic table. Oxygen further to the right, which means, again, it's more electronegative. That tells us carbon is less electronegative. And again, that sort of logic of there's just one carbon, so let's put it in the middle, seems good. And we're going to do some oxygens on each side. We're going to do a single bond. That, again, is 4 electrons, 2 for each line. That means I got 12 more to go. Again, outside in. So 2, 4, 6, 8, 10, 12. At this point, I put on there 16 electrons, yeah? Is everybody good in this case? No, carbon is well short, right? Carbon has only four electrons in this case, right? So again, we're going to make a double bond. It doesn't matter which one you choose. We're going to take a pair of electrons and move it in to do so. That's going to get us here a double bonded oxygen on the left. Did that actually fix the problem? No, it got better, right? Carbon is now up to 6 electrons, right? There in the middle. This case, can I double bond anywhere else? Yeah, I could double bond on the other oxygen. And that is what you would want to do before you leapfrog to a triple bond. Again, you want to kind of exhaust all your double bond possibilities if there happens to be more than one before you go to a triple bond. So we're going to do the same thing. We're going to take a pair of electrons and bring that guy in as well. And that's going to get us now a double bond on each side. And did that fix it? It did. Our carbon in the middle now has 8 electrons. And each of the oxygens on the outside has 8 electrons. So 2, 4, 6, 8. Carbon, 2, 4, 6, 8. 2, 4, 6, 8. Everybody has 8 electrons. And we still have a grand total of 16 electrons, right? Which is what we has to have. Any questions on that, though? Next one there. Rolling through. We got CO3 2 minus. So once again, 4 for the carbon. We have 3 oxygens, each are 6. Minus 2, what am I doing? I am going to add 2. Again, minus means I gained electrons, and 2 is how many I gained. So we do have to add that minus 2 charge into our total. 24 valence electrons here. So we're going to go carbon in the middle as it's the least electronegative. We will do our single bond to everybody. That is 2, 4, 6 electrons. We got 18 more to go. We'll go 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this point, I have now put on there 24 valence electrons. Is everybody good in this case? No, the carbon in the middle is short, right? Again, the carbon in the middle has only 6. Once again, we're going to double bond at any of those oxygens, and that would get us a double bonded oxygen there, single bonded there, and a single bonded there. Once again, since it does have a charge, we'll put some brackets around it and a -2. This is again another one that you could have done a resonance structure by just double bonding at any of the oxygens that you chose. So again, if you chose to double bond to the left, your picture would look something like this. And if you chose to double bond there to the right, your picture will look something like this. Once again, any one of those 3 pictures is perfectly good. And again, if you were asked to draw all of the possible structures, all 3 of the pictures is what you would want to draw in that particular case. Any questions on that one there? All right, so we got, we'll do NH4 plus next. I was going to flip the page, so we got a little bit more to write on maybe. There we go. So we'll go NH4 plus. Again, we got 5 for the nitrogen. There are 4 hydrogens, each is 1. And again, on the plus here, I should subtract 1, right? Because positive means we have lost electrons. So we do need to subtract the electrons out. That's going to give me 9 minus 1, which is 8 valence electrons. In this case, there really is no option other than nitrogen should be in the middle because, again, hydrogen cannot be in the middle for any reason. So we're going to do our nitrogen there, hydrogen's around. We're again going to do 1 single bond to everybody. How many electrons did I just use? That's 8. So I'm out of electrons at that point. Is everybody good? Everybody is good, right? Nitrogen in the middle has 8. Each of the hydrogen has our magic number of only 2, right? Also a little bracket around that to make it look all chemistry like there with a positive charge on the outside. Any questions on that one there? Last one was the nitrogen. And in this case, we have 2 times 5, which is our nitrogen, and that's 10 valence electrons. In this case, there really is kind of no central atom, so you just put them side by side, it's good to go. You could still do the exact same method we've been doing, even if there's just 2. You're going to connect them. That's 2 electrons, which means I have 8 more to go. Gonna just put them on one of them. So 2, 4, 6, and 8 at that point. I am now out of electrons. Is both nitrogens good? Now, the one on the left has only 4 electrons, right? It's got 2 and 4, so it's quite short. The one on the right's good. It's got 8. So here we're going to try to fix it by making a double bond. We're going to take a pair of electrons and bring it in. That will get us something that looks like this. Did that fix the nitrogen on the left? It did not. It got better. It's now up to 6 electrons, right? It's got 2, 4, and 6. At this point, there is no other option for a double bond. So now we're ready to go to a triple bond in this case. And we could then take a pair of electrons and bring it in to make a triple bond. And that is how our friend nitrogen gets 3 bonds there, triple bond between them. And now we have, again, a total of 10 electrons, and everybody has 8. Both of the nitrogen through sharing through that triple bond will reach the octet rule. Any questions on that one there? So again, if you follow these steps, it should lead you to a pretty good structure, probably the right structure that you're going to do along the way. Any questions on that? Okay. All right, so let's talk about a couple other things here. Resonance structures, as we talked about a little bit a second ago. But before that, let's talk a little bit about bond length. And you do not need to memorize any of these numbers. But when we look at this bond length, which is the distance between the 2 atoms within a bond, we look at like a carbon-carbon single bond, it's 154 picometers, carbon-carbon double bond 133, and triple bond 120. If we look at the carbon-nitrogen single bond 143, double bond 138, triple bond between carbon and nitrogen 116. What we actually see is every time you put on an extra bond, everybody gets closer, right? Because as we just saw, we have a single bond like so, and we bring in some electrons to make a double bond. All that electron density is now in the middle. Going to bring those nucleuses in closer to each other. Make a triple bond. Going to bring everybody in. So every time you sort of add a bond, you're making a lot more negative charge between the 2 atoms. Going to attract the positive nucleus and going to drag everybody in closer to one another. So typically speaking, a single bond is longer than a double bond, and a double bond is longer than a triple bond. It's not like a single bond's like our triple bond's 3 times as short as a single bond or anything like that. That also relates to bond strength. A triple bond is actually stronger than a double bond, and a double bond is stronger than a single bond. I think of it like a brand new pencil right out of the box, right? You take a brand new pencil, nice and long, you can snap that thing, no problem, right? You take a pencil, maybe you took a chemistry test with, you got like just an eraser and like a small little nubbin left, right? Good luck trying to crack that, right? Or break it in half. Everything's just too close to each other. And that's sort of the same idea here. A triple bond, because the distance between those atoms are much smaller, everything's locked into place pretty tightly. It's going to take more energy to try to break that than if you have a single bond where it's a little further away from each other, not locked in as tight. Same idea there. A triple bond is not like 3 times as strong or anything like that, but is sort of the pattern that we see. Resonance structures, as we've been talking about, really does develop anytime you have more than one option as to where you could put that double bond. And again, as we saw with carbonate there, and we saw with nitrate, you could draw equivalent structures by just moving the double bond to all really the possible possibilities that it could be at. Again, they are usually separated by this kind of 2-headed arrow heading in both directions if you were to draw all of the structures at the same time. So a couple of examples that we saw there, you don't have to worry about the charges, but again, our carbonate that we just drew, every single one of those, again, you can just move that double bond to all possible location. Benzene ring, we will actually see it when we get to organic. That is the benzene ring. It actually has 3 double bonds in it. Each of those points are actually carbons. These are all carbons here. And they all have hydrogens actually attached to it as well. Most of the time, you don't draw any of that in. It's what's referred to as line structure. It also could be drawn where those triple bonds are basically moved in the opposite location. Probably how you'll typically see it in your book usually is because those electrons are delocalized and moving around, they'll sometimes just put a circle in the middle to indicate that those electrons could be pretty much be anywhere within the ring and stuff like that. So that is benzene ring, which also obviously has a resonance structure to it. All right, so let's talk a little bit about the exceptions to the octet rule and a couple of things important about it, which is in this class, there will be no exceptions to the octet rule. Everything will obey the octet rule. Everybody needs to get to 8. Yeah, nobody should go over 8. Nobody should go less than 8. Everything needs to be 8 here. But in reality, in real life, there are some exceptions to the octet rule that do occur. So you just need to know what the exceptions are. You will not be asked to draw any of the exceptions, but you just need to know kind of what they are. One exception was referred to as an incomplete octet. And much like the name implies, there are some elements that are perfectly fine with less than 8 electrons around it. So beryllium, for example, boron and aluminum are 3 elements that are perfectly happy with less than 8 electrons around them. They're what are known as being electron deficient. I would say in most cases, boron is probably the main example that you see for that, although books do like to use that guy right there as an example. But boron, again, is perfectly happy. As you can see there, it has only 6 electrons, and it's perfectly fine with that. So again, that is what is known as an incomplete octet. And those are really your 3 that typically you think about. Again, beryllium, boron, and aluminum. And out of those 3, probably boron is the most common one that you sort of come across that's perfectly fine with that. Boron and aluminum will pretty much go to 6. Beryllium will go to 4 basically. But again, they'll be happy that way. The other 2 exceptions to the octet rule that you again will not do in this class in terms of drawing, but just need to know, is an odd electron molecule. And much like the name implies, when you add up all your electrons, you got an odd number. And if you're putting electrons on as pairs and you have an odd number, then you got 1 single electron left over when it's all said and done. And that's an unpaired electron. And as you can see here in NO, we got 1. NO2 also have 1 unpaired electron. That happens a lot also in atmospheric chemistry with chlorine, sometimes referred to as free radicals. Yes, they have unpaired electrons. They're not very happy about that, and that makes them really reactive to try to fix that situation, to get rid of that and kind of pair up and stuff like that. Probably if you ever take another chemistry class, the most common sort of exception to octet rule that you come across a lot is the expanded octet. Also found online a lot when you search, so you should be careful when you search to make sure you don't use something that you shouldn't. The expanded octet is a situation where there's actually elements that are perfectly good going above 8, and you could go upwards of 12 electrons around it and be perfectly fine. Those elements that are able to do that is, if you look on the periodic table where sulfur is, and you go to the right and left of sulfur and down, really in the non-metal region. So here's sulfur. You kind of go right and left of sulfur and down in the non-metal region. Those guys can go above 8 and be perfectly happy with that. That is because sulfur is on period number 3. And period number 3, when we talk about electron configurations, is an N is equal to 3 level, right? The 3rd energy level. And if you remember when we talked about electron configuration, what orbitals begin on the 3rd energy level? We have S's, we have P's, and that is the first energy level that you get, D's. So these elements have actually d orbitals available to them to stash all the extra electrons they may need, even if they're not using them. They actually have them available to do so. And that's why kind of where sulfur is, right and left and down, all these guys have d orbitals available to do so. That is also why never ever should anybody above there go over 8, because that is the second energy level. And on the second energy level, there's only s and p orbitals. They don't have the d's available to them, so they never could go over 8, like carbon, nitrogen, and oxygen. They got to stick with 8. But something like sulfur could do it, like SF6. If we just attach and draw a Lewis structure for this, and I'm not going to draw all the dots on the fluorine, but they all have dots around them to complete the octet. 3 and 36. If you just count up what we got going on the sulfur, 2, 4, 6, 8, 10, and 12 electrons around the sulfur, and it is perfectly fine. So 3 exceptions to the octet rule: incomplete octet, odd electrons, and an expanded octet. Once again, to emphasize, everything should follow the octet rule in here. So never do any of these guys. And I say that when I was talking about online for a reason, because let's just say, for example, you went online and you wanted to find the pictures and you search for something and you want to draw SO4 2- sulfate. If you follow the steps that we talked about in here, this is the picture you should end up with. All single bonded. Everybody has 8, everybody's good. There's no need to go any further in this class, yeah? If you Google sulfate, you probably might not get that picture. You might get this picture. Which is definitely going over 8 there. That is the expanded octet version of sulfate, which then your teacher knows you Googled it, because he just told you not to do that. You should end up here and not here, right? So make sure you don't do any of those things, because people sometimes know. Just for a curiosity's sake, why do you see the one on the right? But for reasons not important to our class, the one on the right is actually the better picture of the two, believe it or not. That's one case where actually the one on the right is really the better picture, and that's why you'll actually see it online and stuff like that. But for our purposes here, you should not end up with this picture. This is the picture you should end up with. So make sure that you follow their steps that we talked about to draw them, and that you do follow the octet rule. You don't go over. Any questions on that there? Okay. Okay, the next thing we're going to talk about is geometry, molecular geometry, and we're going to talk about 2 types of names in terms of geometry, and one describes how the electrons are arranged around the central atom, and this is what is sometimes referred to as the electron pair geometry. And for the purpose of this lecture, I'm just going to kind of abbreviate that as EG, so I don't have to write it out all the time. So electron pair geometry, I'm just going to kind of abbreviate with an E and a G, and that's what I'm talking about. And it describes around the central atom how all the electron pairs are arranged in 3-dimensional space, be it dots or lines. It doesn't really matter. It's all electrons that are there. There's also the molecular geometry, which is sometimes referred to as the shape by people. And for the purposes of this lecture, I'm just going to call that the MG again, so I don't have to kind of write it out all the time. I'm just going to abbreviate it with an MG. What does the molecular geometry or shape represent? It represents the actual overall molecule's shape when it's all said and done. And that is based on the types of electrons that are present, how many bonds there are, how many non-bonding electrons there are present, and all those things go into that. These are 2 names that you'll have, and in some cases, the name will be the exact same name, and in some cases, they'll be different in terms of the names. We'll talk a little bit about that. For our purposes, just so you know, you will be responsible for only the molecular geometry name. But I think like the lab and that type of stuff talks about the other ones, so we'll just cover them both. But for lecture, you will just be responsible for the molecular geometry name. All right, so let's get into how we go about doing this. So molecular geometry, again, refers to the three-dimensional shape of the molecules. We can make a pretty good prediction as to what the shape will be based on the central atom. And when you're doing geometry, it's always the central atom that's where you should look. No other atom involved. It is always the guy in the middle that is the most important. If you happen to have two middle atoms, you got to look at them both separately, but it's always the center atom. And it's really based on, like I said, how many electron pairs there are, how many bonds are present. One thing that we know is electrons are negatively charged, which means that when you get a bunch of electrons near each other making bonds, they frankly don't really want to be near each other. They actually want to escape each other as best as they can. The news is they cannot do that, otherwise everything would fall apart. But what they try to do is to keep moving until they can find like a comfortable distance that they're happy with, and then they'll kind of lock into place in that case. So they kind of keep moving. The goal is to try to get us way as far as possible from all the other electrons that are around until they can kind of find a happy medium. So the idea of this is what is known as VSEPR, valence shell electron pair repulsion model, which is hence why it's abbreviated. That is a mouthful. And when we look at this geometry, again, like I said, it's the center atom. And really, there's two sort of categories. A center atom that has no lone pairs or non-bonding electrons. So basically, if you draw the central atom, there's no dots. Yeah, no dots, basically. And ones that do have lone pairs. So if you draw the central atom, you got some dots going on there. And those are the two types of sort of categories that we come across with. When we are doing geometry, and only when we're doing geometry, there are kind of one really important rule to follow, and that is pretty much everything counts as one. So if you got a single bond, you got a double bond, you have a triple bond, heck, you got just dots. Everything counts as one. So everything counts as one electron pair, and it counts as one bond. So when you're doing geometry, pretty much you're just going to count everything pretty much as one bond and one electron pair. Now, the second rule there is not super important probably for us, but as we talked about, you could draw different resonance structures. You can apply this geometry to any structure you draw, and you really should get the same geometry for all of them. So, if you double bond it to the left, or you double bond it to the right, or you double bond it up the middle there, you did the geometry for all those individually, you should end up pretty much with the same geometry for all of them. So it doesn't really matter in that case. But this is the main one. Everybody counts as one. Yeah. So again, it doesn't matter if they're dots, doesn't matter if they're lines, doesn't matter if they're double bond, single bond, triple bond, one electron pair and one bond. All right, so let's start with really the simplest ones we could have, and all the other stuff on this screen you don't have to worry too much about. But the simplest geometry you could ever have is the one with a diatomic molecule. And a diatomic molecule is basically you just got two things, right? That's what it means. You got basically this bond. So no matter what diatomic molecule it is, the only way to arrange two things is a straight line, right? Shortest distance between 2 points is a straight line. And there really is no central atom here. There's just two things. And that would give you a geometry of linear. So it is like a no-brainer. If you have a diatomic molecule and you're asked what the geometry of it is, just lay up linear. It's going to be the right answer. It doesn't matter if it is a single bond situation. Doesn't matter if you got a double bond situation. Doesn't matter if you got the classic triple bond situation. Doesn't matter if they're both the same element. Doesn't matter if there are different elements. Every single one that I just drew there, all the geometries for all those guys are linear because there's just two things. Yeah, so it doesn't matter the bonding's there, it doesn't matter what they are. If you have only two atoms in your molecule and you're asked what the geometry is, linear is the way to go. Any questions on that there? So every single one of those that I just drew, they're all linear in terms of their geometry. Again, there really is no central atom in this case, so it will always line up in a straight line. Now, it'd be great if everything was that easy. Of course, it's not going to be. But when we do have a central atom, or we have three or more atoms, we really want to look at two things when you have three or more atoms. If you have three or more atoms, you want to look at always the central atom, and you really want to count the number of electron pairs there are and the number of bonds. And that's really what you want. You really want to kind of make, honestly, a little table for yourself where you have a number of electron pairs, number of bonds, electron pair geometry, molecular geometry, and bond angle. Not that you have to worry too much about bond angle, but that is the best way to kind of do it as we go through these examples, is to kind of make a table, because most people, myself included, can't kind of visualize three-dimensional space of what everything looks like. So, if you could recognize how many electron pairs it has or how many bonds it has, you basically will know the geometry. And again, even though we're going to talk about the electron pair geometry, you're only responsible for the molecular geometry as we kind of go through it. All right, so let's see how we could do that here. So the first example is this guy here, which is beryllium chloride. It is a incomplete octet. So when we go to do this, again, we always want to focus in only on the central atom. So only the central atom. And around the central atom, we want to figure out the number of electron pairs. And when you're counting the number of electron pairs, it doesn't matter if they're lines, they're dots. Again, like I said, double bond, triple bond, it doesn't matter. In this case, there is one electron pair, two electron pairs. So it has two electron pairs. Something with two electron pairs has an electron pair geometry of what is known as linear. And that is based simply on the fact that it has two electron pairs. What's going to happen with those two electron pairs is they don't want to be near each other. So what they're going to do is decide, we're just going to go on opposite ends of the line there, basically, and get away from each other. That is as far away as those electron pairs can basically spread out and be happy and comfortable with each other. Now, when we talk about bonds, those are the lines only, right? We have one line, two lines, and that is two bonds. So something with two electron pairs and two bonds has a molecular geometry known as linear as well. And that is because as those electrons move away from each other, they actually have some atoms with them. So as they move, those atoms move exactly the same way, and they end up basically on opposite sides of a straight line. So something with two electron pairs and two bonds is known as linear for the molecular geometry. It will have a bond angle, as you can see, of 180 degrees. They essentially get it as far away as possible from each other in this case. Both of those names are the same because the only type of electrons we have at this point are bonding electrons. So as those bonding electrons move, so does the atoms move exactly the same way. And that's why the electron pair geometry name and the molecular geometry name are exactly the same name, which is linear. Any questions on that there? Next example would be a central atom with three things attached, like boron here. Looking at the central atom, we have 1, 2, 3 electron pairs. And we have 1, 2, 3 bonds. Something with three electron pairs, the electron pair geometry is known as trigonal planar, or what is sometimes referred to as triangular. Now, what is happening in this case? Well, we now have this situation where we have an extra bond in there, so these guys are trying to get away from each other. These guys are trying to get away from each other, but on the bottom here, they can't get too close to each other either because they don't really want to be near each other either. So they gotta have to spread out. And because these are bonded electrons, those atoms are going along for the ride the exact same way. And you will end up with a molecular geometry, maybe not surprisingly, the same name there, trigonal planar. It is basically going to make a triangle, right? Which is why it's known as triangular, basically. It will have a bond angle of about 120 degrees. You're not responsible for the bond angle, but that's basically what the bond angle would be, 120 degrees in this case. Same idea as what I talked about. Both of these names will be the same because only electrons here are bonding electrons. So as they move, so does the atoms. They all end up in the same location, and they keep that kind of distance as they can away from each other. Any questions on that there? Next example is one where we have a central atom and 4 things attached. That is really bad. So let me read down. Not sure what happened with that guy there. So let me just redraw methane so it looks a little better. There you go. All right. So in this case, again, looking at the center atom, always the one you want to look at. When you're doing geometry, outside atoms don't matter. Always the guy in the middle. We got 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. Something with 4 electron pairs, the electron geometry name is known as tetrahedral. Some people call it tetrahedron if you're old school, but nowadays books go tetrahedral. In this case, we also have 1, 2, 3, and 4 bonds as well. So bonds are 4. So the molecular geometry name is also going to be tetrahedral. And same idea here. What's going to happen is basically you'll get kind of this deal happening. These guys are going to kind of spread out as much as they can, but we got that 4th bond in there, which means these guys also got to keep a little distance from each other, and they'll end up with this kind of tetrahedral shape that sort of looks like that there. Actually, the hydrogen is going behind the screen as well, if I could draw it right correctly. And it will end up with a bond angle of 109.5. Again, both of these names are going to be the same because we still only have bonding electrons involved. So as they move, so does the atoms, again, ending up in the same location. Any questions on that there? At this point, they have the same electron geometry and molecular geometry because there is no non-bonding electrons on the central atom. It is when we start introducing non-bonding electrons on the central atom that we actually see a change in the name. So when you start putting dots on the central atom, this name actually changes. The electron pair geometry stays the same because it doesn't matter what type of electrons you have for that. But once you start introducing those non-bonding electrons, we actually start to see a change in the molecular geometry. And the reason for that is electrons, because they are negative, could only handle so much togetherness, yes? The best situation for electrons is what we just saw in all those examples, bonding electrons near bonding electrons. They could kind of handle being near each other. But once you kind of move away from that, so that's where you have lines and lines near each other. Once you move away, when you start getting non-bonding electrons and bonding electrons, so dots and lines near each other, they want to get further away from each other. And they're able to do that because the non-bonding electrons doesn't have an atom attached to it. So it gives it a little bit more room to move. Now, when you get to the lone pair and lone pair, that is like the worst situation in terms of electrons being near each other. They're like, I want to get as far away as possible for you when you have dots near dots. They could do that as well because now you got multiple guys that don't have atoms. So it gives everybody a little bit more room. This is why the molecular geometry name is what changes, because as those non-bonding electrons try to get away, the bonded atoms start to move, and we get some different overall geometries of those molecules because we have a little bit more space because not everybody has an atom basically attached to them. So let's see when that happens and what happens in that case. Sulfur dioxide is an example of that. If we draw sulfur dioxide like we did earlier, we will end up with something like this. When we look at the number of electron pairs around the central atom, which is the sulfur, how many electron pairs does it have? It has 1, 2, and double bond counts as only 1, so that's a total of 3 electron pairs. How many bonds does it have? It has 1 for the double bond and 2 for the single bond, right? So that is a total of 2 bonds. When we talk about the electron pair geometry, remember everything counts as 1. So when we talk about the electron pair geometry, that is still 3 electron pairs, which is trigonal planar, like we talked about. Now, the molecular geometry, I personally go with angular for this. Some books go with bent or bent angular for this one. And what happens in this case is we now have those non-bonding electrons. I'll just draw them like that. And what happens is those oxygens want to get away from it as far as possible. So we're going to get a pretty big, I want to get away from you in that case. But again, we then have the bonding electrons that can't get too close either. And we end up with this, what is referred to as an angular sort of shape, or some people again refer to it as bent or V-shaped. And that is why we get, again, a different molecular geometry sort of name in this case. Bond angle is actually based off of the electron pair geometry. It's actually less than 120 degrees. So it's kind of based off of the electron pair geometry there. Question on that one. So again, I go with angular, but again, a lot of books will go with bent or bent angular for that. And there is actually a difference between bent and V-shaped. All right, let's talk about the last two here before you pack up. Yeah, relax. So NH3 is an example here. If we draw NH3, it looks something like this. If we go to the center atom, we have 1, 2, 3, and 4 electron pairs. Remember, when you're counting electron pairs, it doesn't matter if they're dots, doesn't matter if they're lines, everybody gets counted as 1 electron pair, and that is 4. In terms of bonds, 1 bond, 2 bonds, and 3 bonds happening here. So something with 4 electron pairs, the electron geometry name is tetrahedral. And again, in this situation, we have a similar deal. We have the nitrogen that has those non-bonding electrons. And now those hydrogens are going to try to kind of get away from each other and also away from those non-bonding electrons. But again, they got to be careful not to get too close to the other people here. And we end up with a molecular geometry, which is known as trigonal pyramid. And it is that reason because it kind of makes a pyramidal shape when you kind of do that thing. And it looks like a triangle. So important distinction in terms of names. We saw a second ago trigonal planar. And this one is trigonal pyramid. They are different. Yes, you got to choose. You can't just write, by the way, trigonal. Otherwise, I may just have to do that. Don't let me choose. I failed chemistry, so I'm going to choose wrong. Yes. So don't do that. Don't do my other favorite where people are very confident on the first name, trigonal. And then it's like, it's clearly planar, pyramid. So make sure you do choose. They are different. This guy is 3 electron pairs, 3 bonds. This guy is 4 electron pairs and 3 bonds. So there is a difference between those two. So make sure you keep that in mind. All right, we will later.